Section 2.1, Basic Multiplication. Multiplication can be understood in a number of ways. One way is by using a grid, and what the picture of the grid does is it gives us the idea that multiplication is repeated addition. Example, compute 3 times 4 using a grid. So the idea behind using a grid for multiplication is as follows. 3 times 4 means 3 groups of 4. So here's one group of 4. Here's another group of 4, and another group of 4, giving us 3 groups of 4. How many total squares are there? There's 4 here, plus another 4 is 8, and another 4 is 12. So 3 times 4 is equal to 12. For larger numbers, we can think in groups of 10s or even 100s. Example, compute 3 times 40 using a grid. If we wanted to use a grid, we could try to do 1, 2, 3, 4, 5, 6, 7, and try to get out to 40, but that would just take forever. So instead of thinking of 1, we'll think of 10s. 10, 20, 30, 40. Put a little 10 here to remind us that each of these represents 10. And then we have 3 groups of this. 10, 20, 30, 40, and one more. 10, 20, 30, 40. How many do we have in total? There's 40, another 40, and then another 40. 3 times 40 is equal to 120. Example, compute 30 times 40 using a grid. This time, instead of just thinking about 10s going horizontally, we'll think of 10s going horizontally and vertically. So this represents a whole collection of a 10 by 10 grid going in both directions. So going horizontally, 10, 20, 30, 40, and going vertically, 10, 20, 30. So from this row, each of these 10 by 10 boxes has 100 objects in it. So 100, 200, 300, 400, 400, and another 400, and another 400. 30 times 40 equals 1,200 or 1,200. The grid is a tool to help us think about multiplication, but you really need to know your multiplication tables because counting can be very, very slow. Compute 7 times 6. It takes you a very long time to draw out 7 by 6. 1, 2, 3, 4, 5, 6, 7. And then to do this over and over and over again just takes a lot of time. This is why we learn the multiplication tables, and if you learn them correctly, you will know that 7 times 6 is equal to 42. Example, compute 500 times 20. We are going to use a grid for this one, but we're not going to be counting out all the components. 500 by 20 looks something like this. 20 this way and 500 this way. If we were to break this up, we would have 10s going horizontally and 100s going vertically. So each box would be 10 by 100, which means that there are 1,000 in each of these boxes. 500 times 20, how many boxes are there? 5 times 2 is 10, and each one contains 1,000, so we'll put 3 more zeros at the end of it. 500 times 20 is equal to 10,000. Section 2.2, the distributive property, part 1. The distributive property is really just an efficient counting scheme. Example, compute 6 times 43. If we were using a grid, it would look like this. 6 by 43. Now instead of using the number 43, we want to break this up into pieces that are easier to work with. So instead we'll do 40 and 3. Now we can see that this rectangle on the left contains 6 by 40 or 240 pieces, and the rectangle on the right contains 6 by 3 or 18 pieces. So we write this out algebraically as follows. 6 times 43 is equal to 6 times 40 plus 3. And by the distributive property, this is 6 times 40 plus 6 times 3. which is 240, plus 18, which is 258. Example, compute 345 times 6. If we were to use a grid, it would look like this, 345 times 6. How would we break up 345 to make it easier to work with? 300, and then 40, and then 5. And then we would add up all of these rectangles individually. 345 times 6 is 300 plus 40 plus 5 times 6. 300 times 6 plus 40 times 6 plus 5 times 6. 1800 plus 240 plus 30. 1800 plus 240 is 2040, and 30 more is 2070. One quick word on presentation. Some students have learned to do the distributive property by drawing these rainbows. There's nothing wrong with this as a visual tool. However, as far as presentation goes, this is unnecessary and clutters up the page. So if you do this, you will need to erase the rainbows before you turn in your paper.